to really be hosting today's last seminar of the year, and it's the second time we having this a seminar with the let's say our junior GCC fellows here from our institutes. We have Warren and Michael, fantastic presentations you see here. So I'll ask Megan to introduce Warren, and I'll just briefly, on behalf of Holger, introduce Michael for their presentations. Please, Megan.
Right. Good morning, good afternoon. I don't know where everyone's in different places. So it gives me great pleasure to introduce Warren Little to you. I don't know if you can see Warren. He doesn't have a camera on. Warren is a BSc Chem-Eng graduate from UCT in 2013. And then Aubrey persuaded him to stay on to do some masters, to do some interesting research on the vertical roller mill. And as all good research goes, the questions get more and more. And so Warren subsequently upgraded to a PhD. He worked extensively on the vertical roller mill, even got to spend some time in Germany on the device as well. And his thesis went through this year with his examination reports came back, and he will be graduating in December. And Warren is currently a comminution specialist at Kansanshi. And I think Warren is also a bit pushed for time. So if he disappears halfway, you know, site is calling. So thanks, Warren.
Yes, so maybe I can introduce already Michael, and then we can have the two seminars back to back. So very quickly, Michael Klichowicz, he just finalized his PhD last year, 2020. In Freiburg. He has been working with Holger Liebowitz, who's the latest addition to the GCC, and he's a mechanical engineer by training, and he's right now a postdoc in the Freiburg Institute of Mineral Processing. So also, it's a pleasure to mention that he was nominated one of the student, what do they say? IMPC student Young Author Award awardees for the conference that happened that actually didn't happen in Cape Town, but the awards were given. So an opportunity for me to congratulate you, Michael, in person. So I think we can go ahead with the presentations, correct? Warren, please go ahead if you don't mind first, and then Michael. We'll pick up from that. Please, guys.
Sorry, one more comment before Warren gets going. Aubrey sends his apologies. He's currently traveling, but I know he would have loved to have been here to support Warren and Michael as well.
There we go. Can someone just confirm if they are seeing that screen?
Yes, it's just not in presentation mode yet. But
okay, it's probably because I went back to. Apologies for that. I hit F5 and I'm using a browser, so just refreshed everything. You go back to the presentation. Okay, there we go. That better. So
why
again,
are you not sharing your screen?
Oh. Okay, can you confirm that's happening now?
Yes, it's just not yet in presentation mode. We can see your PowerPoint.
Okay. Apologies, guys. There we go. Is that functioning now?
No, but we're just seeing your background. Looking curious.
Warren, do you have an extended desktop? Because I think it's you're sharing the desktop, not the PowerPoint.
Yeah, that's exactly it. Okay, should have logged in earlier. Is that happening now?
Nothing yet.
Crazy. Okay, please tell me that's working now.
Still presenter mode, but
Yeah.
you might have to persevere with that.
Just if you, sorry, Warren, if you just press the F5, it's going to go to the slideshow, then everybody can see the full slide.
Yeah.
Just press F5.
Okay. I think it's because I'm going through a third party here, browser versus a different platform.
Warren, if you can just minimize your slide sorter on the left, just push that out the way and then let's just do it as it is.
Yeah, I think so too.
Cool.
Yeah,
Sorry,
just go like that.
Let's go ahead with that.
Not getting any results. Okay, thanks guys. So sorry for all that mess up. Megan, thanks for the introduction, and everyone else, thanks for your time, which I've sort of been wasting around. So here to present on the vertical roller mill. We'll look at operating the vertical roller mill with different classification devices, as well as just how the vertical roller mill operated in a mineral processing application. So I know this is a global comminution collaborative. Just to prepare you guys, you are going to be seeing some flotation results. But we are at preparation step. So our product is what's needed. And our product's got to be good for recovery. So we can never forget that we're just a step in the process. As Megan already mentioned, Aubrey and Megan herself were my supervisors for the PhD. Which is coming through, I think graduation's like in 2-3 weeks time or something. So just jumping in straight to the vertical roller mill here, for those that are not familiar with it. The vertical roller mill combines, or in typical operation, combines both grinding and classification components. The grinding happens at the bottom of the mill, where we have a rotating grinding table and a series of rollers. Material falls onto the grinding table. As the table rotates, it passes outwards, passing underneath the rollers. So this is grinding components. In at least in airflow applications, we have a dynamic air classifier, which is the top part here, situated above the grinding components. And this is where the classification happens. These devices, the largest devices, can receive top size feeds of up to 150 millimeters. And in a single unit, take the PAT down to 20 microns. So quite a large size reduction there in a single unit. The devices are commonly used in cement and coal grinding applications. And in these applications, they are accepted as being more energy efficient. The dry grinding applications, they are more energy efficient than conventional tumbling mills. So the increased energy efficiency there sort of coming through from the lower specific grinding energy. We have a direct application of force from the rollers to the particles, unlike conventional mills where we have energy transfer to steel balls, which then fall. We have a lot of excess energy wastage, so direct energy transfer here. The one drawback with these devices is that they also have high classification energies. The dynamic air classifier, typically much higher classification duty than anything we are used to in a mineral processing application. So running through just flow of material in these devices, for those unfamiliar, again, I'm sure many of you, this will just be a rehash. We have feed there in red coming through and falling onto the center of the grinding table. As the table rotates, material passes underneath the grinding rollers, so passing between the rollers and the grinding table, and here it is compressed. So we have interparticle breakage occurring through compression. At the edge of the table, material falls off the table, and in airflow operation, which is the figure here shown on the right, the material is suspended in a stream of air. The stream of air carries material up to the dynamic air classifier. The product size material passes through the dynamic air classifier with the flow of air, and the dynamic air classifier rejects the coarse material, which is recycled back to the grinding table. So just one other thing to point out here is just that there's a little black arrow there at the bottom, unsuspended material. So if any material in airflow operation is too coarse to be suspended by the flow of air, it falls to the base of vertical roller mold and then is recycled externally. When we look at operating this machine in overflow mode, this is the stream that we are making use of. We don't push air through the mill, so there's no suspension of particles within the grinding chamber, and all the particles fall to the base of the mill and then get recycled externally, passing it through external classifiers. So I did an extensive amount of work in operating the mill in airflow mode. Looked at changing things like such as dammering height. Dammering height there is just a wall at the edge of the grinding table, which affects the retention of material on the grinding table, affecting things like the retention time on the grinding table as well as bed depth. Also changed the grinding pressure, so the forces that the grinding rolls exerted on the material, as well as changing the target P80. The P80 here was determined, or was targeting a P80 was achieved by varying the dynamic air classifier rotor speed. So we kept pressure drop and airflow rate across the mill constant. Just varied the dynamic air classifier rotational speed until we achieved the product P80 we needed. So from this initial test work, we got a large number of products. Some of the interesting observations or interesting findings from this were that when we increase the compressive force, the grinding pressure exerted on the rollers, or exerted by the rollers in the particle bed, we developed a finer product. So while we are maintaining a relatively similar P80, we get a less deep particle size distribution with a greater portion of fines. So I think, yes, the fine screen size 25 microns. So this was for increasing grinding pressure. Similarly, when the dammering height was increased, we also found that for a similar P80, we got an increase in proportion of fines generated, so less deep particle size distribution. The thinking here is that when you increase your grinding pressure, you're increasing the forces exerted through the particles on each pass under the grinding rollers, higher force, we're going to generate a smaller product particle size distribution from the grinding table, and this will be presented to the gasifier and affect the product from the gasifier. For the dammering height, rather than more forces applied or more force applied, it's a greater number of compression events before the material leaves the grinding table. So it's just something to bear in mind. We'll come into our flotation discussion shortly, that the dammering height, high dammering height and high grinding pressure produced a finer particle size distribution. We also did some mineralogy test work here, just looking at the PGEs, just the liberated, associated, attached and locked. If we look at the two outer bars and the central bar, this is for varying target P80 at a single grind size. And as we grind finer, yes, we do get better liberation. Just having a look at the initial, or the first, or the three columns in the center there, that's for different dammering heights. So when we have an increase in dammering height, we see, well, from this data, it looks like there's a decrease in the amount of liberation. Yeah. But if we look at the recoverable PGMs, if we were to include the associated PGMs with liberated base metal sulfides, we actually see an increase in recoverable PGMs as the dammering height increases. And this would follow our expectation as we grind finer, or as we're generating a finer product at higher dammering heights, so we should have a slightly better liberation profile. Moving on to the flotation results, yeah, things don't necessarily agree with what we would expect, and it required a bit of thinking about the process. When we increased our grinding pressure, our recoveries actually dropped off. So for all the results, all the flotation tests that we had, grinding at a lower grinding pressure, say 600 kilonewtons per meter squared, produced a higher recovery of the PGEs and also base metal sulfides for that fact, than the higher grinding pressures. The same is observed with dammering height, a bit less variation between the 4 and 7 millimeter dammering heights. But as dammering height increased, we dropped off in PGM and base metal sulfide recovery. As the recovery is dropping there, the grade's going higher. Just the general inverse relation you would expect for flotation. So after a lot of querying this data, not really showing us what we expected, what it came down to, and where we saw the differences is also in the solid water recovery, coming down to an issue of froth stability. So we have two pictures there on the right. This is for a 75 micron P80 at a dammering height of 7 millimeters. And on the left, we're at a lower grinding pressure than on the right. So this is the first concentrate collected. So very, very high loading here for PGEs. And I'm sure you can all see a very visible difference there in the bubble structure. The stuff at lower grinding pressure, a lot smaller bubbles, and it looks like a lot more moisture, a lot more liquid, a lot less solid loading. So what is effectively happening here is we have a very high solid loading when we are at higher grinding pressures, the same for higher dammering heights. And this is actually destabilizing the froth and causing a reduction in solids and water recovery, which is affecting our valuable mineral recovery. This higher solid loading is linked to that increase in proportion of fines that we have when grinding at higher pressures and high dammering heights. So although we have a similar P80, we're generating more fines which are reporting to the froth and destabilizing it. So one thing just to note here is that we just used a standard flotation reagent suite here that was typically used by Anglo. research for their bore flotation, and something that I suppose it's another PhD right here, just another option looking at the dry versus wet flotation recovery, and the need to optimize reagent suites for the vertical roller mill, if it's really going to get given a true comparison. Yeah, so just expectations there being overshadowed by froth phenomenon linked to the increase in fines portion. So moving on to the external classifiers. So this is using that vertical roller mill there in overflow mode, where we have external recycle stream. We fed that to a vibrating screen here, dry vibrating screen. Aperture size there was 500 microns. We also fed it to external hybrid air classifier. Hybrid air classifier because it combines static air classification and dynamic air classification. The reasoning here for these two devices is to try to target lower energy duty classification techniques, so that high energy, specific energy that's required for classification of the dynamic air classifier is reduced, so we can further benefit from the reduction of specific grinding energy. So for the static air classification portion here, we have material falling. It's a bit highlighted in green here, or in green. We have material falling through a cross-sectional flow of air. And as this material falls, the coarse material falls is not deviated by the airflow. And the intermediate and fine particles reach the dynamic air classifier, where the product size particles will be separated and continue out of the air. So going here to the particle size distributions from the various classification tests. We have on the left the screening and internal airflow particle size distributions. This at the coarse grind, so targeting a PAT of 240 microns. We did do screening tests at two different grinding pressures. Looking here at 600 kilonewton per meter squared, getting a very similar or a similar P50 value there, but on the coarser side we are seeing a split in the PAT there, with the screening particle size distribution having a coarser product. On the right hand side we have the comparison between the external and internal air products. At the finest grind, the PAT there of 60 microns, we see quite a deviation between the external and internal air classification products. The external air product has a significantly coarser component in the tail. So where the internal air classification product has pretty much 0% plus 150 microns, the external air classifier product has about 5%. Target of 75 micron PAT, both the internal and external air classification PST is very, very similar. Looking at the throughput of the two circuits, we see the external air classification circuit having reduced throughput, lower throughput than the air classifier, the internal air classifier. And for the screening, as is expected, the 600 kilonewton having a lower throughput than the 1000 kilonewton. How this translates, into specific grinding energy, we see that the external air classification specific grinding energy here, the green line, is higher than that which is obtained for the internal air classifier. So having similar power requirements, the two circuits, but the reduction in throughput or the lower throughput for the external air classifier showing up as a higher specific grinding energy. So this is just specific grinding energy. The gasification energies just weren't shared with us, weren't shared with me for this. But what I did do was scale this data just based on pilot scale data from Van Drannik on his work on a sphalerite ore, just where he had access to the grinding and gasification specific energies, and just using that ratio to estimate gasification energy. So this is pilot scale here. So this is estimations of overall specific energy in this figure here. And we see that the external and internal circuits are a lot more comparable. The specific grinding energy, for screen is still just specific grinding energy there. Didn't factor in the gasification energy. So for the air classification, it seems like at the finer end of the grinds, we're not seeing much difference between the two external and internal air classifiers. But at the coarser end, we are seeing improved specific energy for the external air classifier and vertical roller mill. So, I mean, I suppose if there's any interesting graph that comes out of this, this is probably going to be it. So now just overlaying, we've got this ball mill grinding energy there. So this is actually the operating work index taken from the plant. So from Klichowicz, the three different target or three grinds that they're three target P80s they are trying to achieve with the units there, and just overlaying that on the specific energy of the pilot scale devices. And throughout the grinding energy, we can see a reduction, or that the specific grinding energy for the vertical roller mill with classification is lower than that being achieved on site. And as I'm sure the suppliers will tell you, and Hakan, if he's here as well, this is pilot scale, and typically at pilot scale, the classification energy, or the ratio of classification energy to grinding energy is not the same as when you move to industrial scale. So we'll probably see a reduction in overall energy, specific energy, if these devices were industrial scale, just because the ratio between grinding and classification energy changes. So also did flotation test work on these samples, not necessarily as interesting as the airflow test work, but we found that the screening products were less floated less well, or we got lower recoveries for them than the internal air classification test work. That most likely due to that difference in particle size distribution, where we had a coarser component for the screening product and the internal air classification product. For the air classifiers, we see, looking at the finest grind there, the P80 of 60 microns. We see the internal air classifier recovery higher than the recovery for external air classifiers. This again linked to a particle size distribution change. So the external air classification product significantly coarser, or having a significantly large coarse component, which likely would have had less liberation than the internal air classification product. If we look at the center figures there, the 75 micron P80s, this is where we had almost identical particle size distributions, and we're seeing an improved recovery for the external air classifier product. So, while this is just one data point, it does potentially show something that's interesting. Maybe if we're able to match particle size distributions a bit better, we'll see the external air classification product working better than the internal product. But really, from my results, not really able to conclude anything in that regard. Also compared flotation performance versus conventional milling. So this is just a tumbling mill, laboratory scale tumbling mill. And for all the grinds achieving significantly higher recoveries, despite that those poor froth stability for the internal air classifier vertical roller mill setup and the tumbling mill products. So maybe at the coarse grind we're a bit more comparable there, but at the finer grinds, the 60 and 75 micron, we're seeing a large difference in recovery. What this is coming down to, and apologies guys, this is now we're going into flotation here. This comes down to the lower oxidation pulp potential for the tumbling mill products, which is affecting the xanthate absorption onto the surfaces there. So it's your 3 lower figures here. It's your ball mill products versus us, just one vertical roller mill product here. So significantly higher oxidative potential. And again, just highlighting the need or the consideration that needs to take place when comparing vertical roller mill or any dry grinding products to that for conventional wet milling systems. Yeah, so that's it. Thanks so much for your time. I hope I didn't overload you. The problem with a PhD, so many results. I want to share all the important ones.
Yes, thanks, Warren. I think we can go straight to Michael's presentation and then take questions afterwards. Shall we do that?
Okay, so possibly I could say then, if there are any questions, maybe just mail them to me. We are down on one of our milling circuits, just gone down for a carbon brush, and I am actually needed on site.
Oh, so you cannot really go. Okay, thanks. So just in that case, if there's any question that can be made on the run here, are you still a couple of minutes available, or shall we really just move on to Michael's presentation? No, so since Warren, you're on the run there, thanks a lot for your presentation there, and please go ahead and go for your work there. And people, please, if you have any questions for Warren, please write them down, and he'll be happy to answer. Thanks a lot.
Thank you. I'll put my mail in the chat. I'll do that before I go. Thank you all.
Please do. Thank you. So we can now go to Michael's presentation, please. Go ahead.
So hello, everybody. Do you see my presentation?
Yes, perfectly.
Okay, then thank you for the opportunity to present what I did during my PhD research. And this presentation will be about modeling of realistic microstructures on the basis of quantitative mineralogical analysis. But here in this presentation, I will actually concentrate really on modeling the microstructures and what we see in the right images. That is just in the outlook here, but we can discuss maybe in the questions. So what is the idea? Oh, yeah, that's the contents. What I'm gonna speak about is the first point, why we need models of realistic microstructures, why are they of interest, and what is the basic idea of the research I did. I want to speak shortly about the methodology that was used here, and in the end we will just have a short outlook on where we can use such microstructures, and of course we will speak about the outcome. What is the research gap? And the research gap is probably the most important point for any PhD thesis. And the research gap I worked on is that we're actually not able to predict the comminution behavior of rock material at the level of the single particle and below. So if you have like this limestone and you want to crush it, you can do this and you will have some crushing result. But if somebody asks you, can you simulate it? then you get in trouble, because you can do some simulations, but you will never have the same outcome as in the real experiment. And that is always not, or that is some kind of problem for us. And there are many approaches for simulating comminution, and maybe one can is the bonded particle model, which can be applied in DEM, and that can be used to explicitly simulate the breakage of single particles. And I think everybody knows, if you have a bonded particle like the blue one, and you apply some load, and you have the correct good material loss and a good parametrization, you can break this particle into the red and the green one. And if you continue in your simulation, you can even break the green particle furthermore. So that is, in short, the idea of a bonded particle model. And there are challenges for us if we want to use such bonded particle models. The first one is we have some kind of excessive computation, or some excessive computations are needed if you want to run simulations with high numbers of particles. Maybe that can be overcome with the increasing computer capabilities in the future, but it is still a need for any researcher or every engineer using such simulations to use as little particles as possible. The second big problem is the adjusting of the internal model parameters, like the springs or dampers. Here on the right, we have an example with two particles which are connected by springs. So if you want to do the simulation, you need correct constants for those springs in order that the model behave like real or realistic material. And if we have our model parameters, we need to validate the correctness of the models and the assumptions. And actually, that is often quite difficult, since we can only validate, or we often have to validate the models with real experiments, and from that we have to use our observations and fit the models to the observations. So it's kind of tricky and sometimes an inverse problem. And the last point that is my research gap, or the gap I worked on, is that for our materials, often the internal structure, the microstructure of the minerals has a high influence on the behavior of the material if it is comminuted. So if we go for any models, if we want to model something that is connected to the grain size level, like selective comminution, for example, then we need to consider the complex mineral microstructure. And the initial idea was that we can use quantitative microstructure analysis, or some kind of image analysis, for example, to characterize the microstructure of our material. And based on this results, it should be possible to model a synthetic microstructure, which can then be used in the simulation. So for this example here at the bottom, we have a hard rock, which has a fabric, which you can see in the microscope, for example, and we can analyze this microstructure with some certain technique, and we get quantitative numbers for the mineral content, for the grain size, grain surface, and so on. And based on those numbers, which are very important for us engineers, it should be possible to create a realistic model of the microstructure, and we can use this model of the microstructure to draw synthetic microstructures at the computer. And those synthetic microstructures should have the same characteristics as the real microstructure, although they are random. So we should be able in the end to create as many synthetic microstructures as we need for any simulation. And then we can just map the microstructure to, for example, an DEM simulation or an FEM simulation, or to whatever simulation we want. But the point is we have realistic random microstructures. Just a short outlook. What is the QMA, the quantitative microstructure analysis? This analysis is based on the typical analysis of mineralogists. We take a representative sample of our hard rock, and then we cut 3 orthogonal slices of this hard rock and prepare thin or polished sections. And then we can analyze those sections under the microscope. And in the results, we can obtain characteristic numbers, for example, for the volumetric content, for the grain size, roughness, and can use those numbers for characterizing the ore or for further processing and modeling the microstructure. And the starting point of my procedure was I thought about how would a human create a 2-dimensional microstructure. Since I thought I will start with a 2-dimensional microstructure and try whether it works or not. And I just imagine you get the task to draw or to create a microstructure that is random but comparable to this given microstructure. And you will probably take a blank sheet of paper and take a pencil, and then you will start draw grain by grain. For example, you start with this grain and add another. And at some point you are at this grain here in the middle, and you're just drawing the grain. And while you're drawing, you're always comparing your grain you draw with the grains that are given. And in the end, you will have drawn some grains on your sheet of paper, and optically it will be somehow comparable to the given one. And in order to minimize the edge effects, you will probably cut off the edges so that you get finally a drawn image that is comparable to the real one. And the question is, how can a computer do the same, or can a computer do the same? And I came up that it should be possible for a computer if we train a computer how to draw a grain, and that can be done with polygons. So if we take a coordinate system and tell the computer where he has to set some vertex and draw a polygon that is comparable to a given grain, then we should be able to teach the computer to draw microstructures. And as I said, I start with 2-dimensional microstructures here, but in theory, it should also be possible to teach a computer to draw 3-dimensional polyhedrons. So from now on, we concentrate on 2-dimensional first. And if we think about a synthetic grain, and I explained to you how to draw those grains, then it is possible to start, for example, with quadratic grain, and we can rotate the grain, we can increase the size, or we can change the angularity between a circle and the square. We can, for example, change the length ratio, or the number of vertex, or the roughness. So we have many parameters we can fit, or we can use to adapt the grain to our needs. And with this approach, it is, for example, possible to draw an elliptical grain, or a star-like grain, or some more realistic angulated grains like shown here. So at this point, we teach the computer how to draw a grain, but the more important step should be to teach the computer to draw a realistic microstructure. And how can a computer draw a microstructure? If we think about this image here, there are 3 given grains, and the computer has the task to draw a new grain, that the program will first look for a free spot where the computer can set an seed point, and that will be the seed point for our next polygon, which will be the next grain. And on the basis of this seed point, the computer will start to draw the polygon as we have just learned. And during this drawing process, the computer will adapt the new polygon to the existing structure. So, for example, the first point, that is a free point, it is set by the parameters for the grain, and the red point here, that is a point that collides with existing structures, and it is adjusted to the existing structures. Here we have again some free points, so the points are set according to the parameters we have chosen, and here we have again a point that is adjusted to the structure, and the blue one, that is a point that is snapped to the structure because it was originally too short, but in order to since we don't want to have very small voids between the grains, there's an edge snapping mechanism that fits the point to the existing structure. And in this procedure, a new grain is drawn, and when it is finished, the program can look for the next free spot for the next grain. So that is the basics of this procedure. And what can we do with this procedure? Here are some example microstructures. So here we have they are all drawn with the program, and we have a microstructure here with more or less equal sized grains. And in the next microstructure, I just changed the variety of the grain size. And you see, in comparison, you have much larger grains here. Yeah, and for example, at the bottom side, I used elongated grains for this example, and on the left side, they are all orientated in one direction, and with each next image, I increased the variety of the orientation, resulting in a more or less unorientated microstructure on the right side. But what else we can do? Of course, we can draw microstructures with a matrix, that is, for example, this orange face here, or we can use, or we can create also pores like those gray structures in this microstructure, and we can add as many faces as needed. For example, we start here with a monomineralic microstructure, which is indicated by all the green grains, and then we add some a blue face, which has smaller grains, and a third yellow face with small grains, and here we have fourth red face with some bigger grains. So we can create random microstructures with as many faces as we want. Now the question is how we can model a more or less realistic microstructure. So for example, we have here this real sample of granodiorite, and the question is how we can create a realistic sample or realistic random microstructure. So first, we have to synthesize a microstructure, and then we have to do the analysis of the microstructure, and we can then, or based on the real sample, we do the analysis with the QMA, and we get the numbers for the grain size, for how many grains, how many faces we have, and so on. And then we can estimate the parameters for the synthetic microstructure. Then we create a synthetic microstructure and measure the synthetic microstructure again. And then we compare the results for both microstructures and synthesize And if there's no fit, if it is insufficient, we have to adjust the synthesis parameters. And we do this as long as the synthetic microstructure is not what we expected. But if we do it good enough, then we have at some certain point a microstructure that fits our needs. And I will show you this at a little example. Here we have in granite, and that is a thin section, which is, and the image came from polarized microscopy. And here I created a false color image of the minerals. So blue, that's all feldspar, some mic, the red are quartz, and we have some opaque minerals, which are not of further interest here. And that is again the real sample, and I used my program to create a synthetic microstructure. And now there's the question, is it a good fit or isn't it a good fit? Maybe some of you think, okay, there's enough blue, there's enough red, so it's a good fit. The next one says, okay, maybe there's some differences in the blue grains. They are not that sophisticated or that structured like in the real example. So the point is, it's really hard to compare two microstructures, since we often use just verbal description of microstructure. At this point, we came up with the idea of a statistics professor who told us, okay, it is possible to use so-called Monte Carlo tests to compare microstructures. And what we did is, we did 999 simulations with equal parameters and created 999 synthetic microstructures. And then we plotted for example, the grain size of all those microstructures, which are here in gray, and we added the red microstructure, which we measured. So that is the grain size distribution of the feldspar of the real example. And if we assume an error probability of 5%, that yields that the lower limit is 25 and the upper limit is also 25. So the distributions which are larger, or if our real example would be out of on the right side or on the left side of those black curves, with the lower or the upper 25 limit, then we would have a bad model fit. But if we are in those limits, we have from statistics point of view a good model fit. So what we see here is that we are quite good in the ranges. But we can dig further in such statistics. For example, we can use those statistics and Monte Carlo tests to evaluate the measures of the QMA, for example, the median grain size or the standard deviation of the grain size. And here we have box plots of the 999 simulations, and in red, that is the real tested microstructure. And we see here again that our real microstructure is in the range of what our model, of what we have simulated with our model. However, that is still hard to compare, since this approach is linked to this QMAs. If somebody else uses other approaches to characterize a microstructure, other figures would result. And there's another even more standardized approach in statistics, and that is point process statistics. And I applied this point process statistics to validate whether the microstructures are comparable or realistic or not. And the idea is pretty simple. If we have such a microstructure, we replace each grain by a point. For example, if we have this red grain here, we take a bounding box of the grain, and replace this grain by the middle point of the bounding box. And additionally, we can add size information to this point, for example, by using a bigger red mark for a big grain, or a smaller red mark for a smaller grain. So we just replace the real microstructure or the simulated microstructure by this point pattern. And for such point processes, there are statistics which are really standardized. And then we can work with standardized statistic methods to analyze whether we have realistic or not microstructures. And I will focus here on 3 approaches. And the idea of each of those approaches is that we take all points after each other. And if we have one point here, for example, if we have taken this point, then we analyze what happens in certain distances r from the point. So at the beginning, we look what happens at small distances r, and then we increase the distance, and we increase this distance until we have covered the whole image. So I have here the results for feldspar and quartz, so the 2 phases with the highest portion on the microstructure. And the first measure is the pair correlation function, GR. And what we see here is on the x-axis, we have the radius r. That's the radius of our field of interest that starts in the middle on the grain where we're just looking, and increases with a higher radius. And this pair correlation function, that is the average number of points in a distance r, and it represents the variability of the interpoint distances. And for random processes, so if you're a random Poisson process, that is always 1, and it is large for clusters. So what we see here, for larger distances, it converges to 1, so it should be a random point process. But for smaller numbers, for smaller radiuses, it is higher than 1, which indicates that we have some sort of clusters in our microstructures at short distances. The second measure, that is a so-called mark variogram, and it characterized the similarities of marks. So marks are here the grain sizes, the grain areas, and it converges in the end to the variety of the marks, so to the variety of the grain sizes. But smaller marks, smaller values of this gamma indicates that we have similar mark sizes. So we have very small values for this measure at the beginning, which indicates that we have that grains which are near or next to each other tend to have similar sizes. And the last measure, that is the mark correlation function. It characterizes the size of the marks as function of the interpoint distance. And that is, we have small marks for small values for small marks, and bigger values for bigger marks. And here we see that for small distances, we have very small marks, which means that we have smaller grains at smaller distances. So I know it's a little bit complex if you're not used to point process statistics, but what we see here is that we have our gamma and our KR, for example, are small for small values, and that indicates that grains which are close together are of similar size and are very small, and that is somehow well, that indicates the natural fact that grains which are close together have to be small since they cannot overlap. Furthermore, we see that our measured real example is nearly always inside the model, which indicates, or inside the simulations, which indicate that we don't have the, that we have a quite good model for our granite here. Okay, so now we are at the point that we can say with those measures we used, we can state that we have a realistic microstructure. And now I just want to give you a short outlook how we can use this microstructure. This is a GM simulation of a plate, of a very thin plate, which is loaded by a chisel in this notch and then fractured. And what we can do now, what I've done now is I've mapped this realistic microstructure to this GM simulation. And then I just varied the strength of the grain boundaries. So if we have a so-called grain boundary factor of 1, all bondings are of comparable strength. So there is no differences in the strength of grain boundary bondings and boundary bondings inside a grain. If we have a lower factor, a weak grain boundary factor, that means that our grain boundaries are much weaker than the bondings in the grain. And if we have a high grain boundary factor, our bondings between the grains are much stronger than the bondings inside the grains. And here that is the proportion of grain boundary breakage of a real experiment, and that is about 55% of the breakage went along grain boundaries. And we can now compare this to the proportion of the grain boundary breakage in the simulation. And we are somehow in between factor 1 and 0.6. And of course, we can now do some parameterization and find a suitable grain boundary factor which imitates this real breakage process, which is somehow in between 0.825 and 0.85. So we have weaker grain boundaries in the simulation, and we use this realistic mineral microstructure. So let's have some short conclusions. We are able to synthesize realistic two-dimensional microstructures on this QMA basis, which is some sort of image analysis. We can import the microstructure into a DM environment. Here I used Jade, for example. We can map this microstructure onto the packings of the discrete elements, and we can model the differences in the micromechanics with an empirical factor that was just presented here in the Outlook. And what I concentrated more here is that we are able to simulate the fractal behavior of randomly created and realistic microstructures, and we analyzed how, and we can use, for example, point process statistics to analyze whether we have realistic microstructures or not. Okay, just in the end, I want to acknowledge that this study was founded by the German Foundation for Research, and I want to thank you for listening to this presentation.
Thanks, Michael. As Marcelo had to leave to lecture, so I'll take over from Marcelo. Really interesting trying to get the interplay of microstructure in with how a mineralized rock fragments, which interestingly, we basically ignore in mineral processing. They just say it breaks into smaller sizes when what we want to do is liberate minerals. And that really is the objective. Can we start understanding that process? So I know with our delays at the beginning, we're a bit over times, but I'm sure Michael's happy to stay on to take some questions. If for those who are able to stay on, those who need to leave, that's fine. And thank you very much for joining us to interesting presentations. So do we have any questions for Michael? Hopefully I'll see you put up a hand or something like that from the screen. Gallery, there we are. All is quiet out there at the moment. David. There we are. David Seaman, you can go ahead.
Hi, Michael. Thanks. Yes, and just confirming Malcolm's comments there that this idea of breakage not being random is obviously we expect to be happening. So good to see that the science behind it. Look, just a very simple question. I'm just wondering what kind of dimensions you were looking at in those microstructures. If you could give me an idea of what size those graphics of yours represented.
Yeah, for example, here we our dimensions of the smallest grain, or no, whether we concentrate on the simulation. Here the smallest grain was about 0.5 millimeters, but it really depends on the DM simulation you run. You can just increase the number of particle or number of DM elements here, and then you can go for smaller microstructures.
Oh, excellent. So you can basically just change the resolution to suit your experiment. Excellent.
You
Thanks.
need a bigger, faster computer.
Yeah, yeah. I suppose just a quick follow-up, if I may, is just wondering if you've been able to look at the simulation or comparison to real life of grain boundaries between different minerals. So I would expect some minerals to have stronger grain adhesion and compared to other coupled minerals.
We didn't do this with this simulation or in this experimental study, but that is possible. I did it for one experiment, but if you have, for example, 4 or 5 different mineral phases, that is a whole lot of work to analyze, since you have quite a lot different bonding types then. But that is something to do. We want to do in future. We just wanted to analyze whether this approach is usable or not with this very simple experiment.
Great, thank you.
Welcome.
Yeah, it's a good question, David, because it could be mineral A and B have a strong bond, and mineral B and C have a weak one. But as Michael says, that computation or mathematically setting it up, and you've got so many variables. If you had some kind of input, Michael, maybe from your experiment where you could pick up preferentially breakage between B and C, that would help guide you, I suppose. Instead of a random study, you would kind of pre-parameterize a bit.
Yes.
Yeah, it's a really difficult problem, and maybe that's why people have avoided it. To me, that's where we need to go to lift our game, and where the objective of comminution is to liberate or expose minerals for recovery rather than just make the rocks smaller. You got any other questions for now? Okay, Michael, maybe you could do like Warren did, is put your contact in the chat if people want to send you a question later. That would be great.
That's no problem.
So maybe on that, we can close for tonight for me, for morning for some of you in South America and North America. Thanks for joining us, our last one of this year. And as Marcelo commented in the chat, we'll be back in February with a new sequence for next year. And we'll also be supplementing that with restarting a series of education, covering the whole comminution field from the mine through to recovery. Those will start next year, which will be for members of the GCC. So membership will be becoming formalized next year. It's been informal this year. But these type of seminars will remain open for anyone to come along to. So thanks for joining us. All the best in the Christmas season, and we'll see you, hopefully catch you all next year. So cheers from the GCC team.